Interpreting position time graphs. Let's start out by highlighting the axes of our graph in red and blue. And this will help us tell the difference between our two variables. So I'm noticing up here at the top that we have a definition of something called displacement. That could be useful. I see a chart of information. Here are some positions, here are some times. I know that time is always the independent variable and it always goes on the x-axis. So I'm going to put t in seconds like this. And I see that position in meters is also listed, and position is marked with an x. X marks the spot. Okay, now it looks like my cat is roller skating again, and she's roller skating down a marked sidewalk. She was observed to be at the following positions at the times listed in this chart. So at the exact second that we started observing her, she was at a spot called 10. And then it looks like she travels along, and at maybe 10 seconds later, she's at a spot called 30. One thing to notice is that her first position is not 0, which we're sort of accustomed to. So it looks like we're going to have to really understand what we're doing here to make sense of this trip of this cat on roller skates. So it says here to plot a position versus time graph for Patsy's motion on the graph above. Use pencil. Okay. I'm going to scale the time axis quickly here. You don't have to label every single marker like you did in 7th grade. And I'm going to go up here, and it looks like if I go up by 5s, I'll make it. Okay, there's that. I'm going to break my own rule here so that people can see it on the screen. Okay, so let's graph our points here. I'll use green ink so it really stands out. At a time of 0, she is at a position of 10. So here's the starting point. So this line is going to be interesting. At 1 second, she's at 12. That's about here. And I'm suspecting that her motion is constant and linear. 2 is 14. That puts her about there. 5 puts her at 20. There. 8 puts her at 26, which is about, there's 25. That must be 26. And 10 will be at 30. And my invisible straight edge will do that. We can now calculate her displacement. You can look back up here and see that displacement is the change in position. So she started here and she ended here. Because remember, this is the path that she followed. So she started at 10 and went to 30, which means that this value is our x2 and this value is our x1. So we can do x2 minus x1, and that will give us our delta x, which is called displacement. And if we plug in the actual values, we end up with 30.0 meters, and we subtract 10.0 meters, and that gives us 20.0 meters. And that is her displacement. So I'm going to write that in, 20.0 meters. And just for fun, I'm going to divide by the time, 10 seconds, and I'm going to stealthily, cleverly figure out that her speed is 2.0 meters per second. So here's the answer, displacement, but we also kind of figured that out, which is always a useful thing to know. So now we get down here to letter C. And letter C tells us how far from the starting point was she at t equals 6 seconds. So at 6 seconds, we could go up, we could hit the line, we could go over and estimate what that value is. It looks like it's about 22. We could also do some fancy math work in the table here and figure out what it would be. But notice that I also have figured out her velocity over here. So if she goes 2.0 meters every second, and she has traveled for 6 seconds, we could multiply this out and figure out that she has traveled 12 meters in 6 seconds. That is 12 meters from her starting point, which was a position of 10. So if she started at the 10 and she went 12 meters, that's going to put her at a position called 22. So her position X is going to be 22 meters at t equals 6 seconds. Her average speed, that would be the total distance she traveled divided by the total time. I figured that out up here, but I'll show that to you quickly. Total distance traveled, she started at 10 and went to 30. That means 20.0 meters. And it took her 10 seconds. So that gives her an average speed of 2.0 meters per second. Is her speed constant? Yes, it is, because the line is straight. And a straight line on an xt graph represents constant motion. Figure out the slope of the line. Well, we could do rise over run, or the fancy equation that you probably learned in math class. Remember, these are coordinate points, and don't confuse these x's with this x, which means position. So you could put in a variety of points here, and you could figure out the slope of the line. I guess you could pick this as one point, and this as another point. So I guess y2 minus y1 would be 30 minus 10. 30.0 minus 10.0, and then that would be equivalent to 10.0 minus 0.0. I feel like I've done this before. And you do all the math nonsense, and it should spit out a value of 2.0. So the slope of your line is 2.0. And wouldn't you know, that's your average speed. Remember, this is your change in position. Position is on the y-axis. This is your change in time. Time is on the x-axis. So when you do the slope of the line, and each of these axes represents something, it's really the same thing as figuring out the average speed. So the slope of the line is the average speed. Now you can do a math equation. Well, the first interesting thing is it looks like this line intersects with the y-axis here at a point called 10, which means this is going to be equal to 10. We've just figured out that the slope of the line is equal to 2.0, which means this expression can be simplified and rewritten as y equals 2.0x plus 10. And this, my friends, represents the motion of a cat on roller skates.